So we are going to be solving algebraic equations with variables on both sides of the equation. And Bethany is extremely excited about this. The fluorescent sheep, yes. All right. So let's take a stab at this. All right. It's not as difficult as you think. I think. I mean, I don't know what you're thinking, but it's not as difficult as you think. So whenever we're solving an algebraic equation, our goal is to get x all by itself. Okay? So our first step, well, sometimes our first step, sometimes it comes a little later, but we want to get all of the x's on one side of the equation. So we're going to have to move one of the x's. Now we don't necessarily have to do it first, but we can. In this case, you could pretty much move anything you want first. But if we want to get the x's all on one side, we're going to have to move one of the x's eventually. So let's start with that. Which of the x's do you want to move? The 8x? Okay, so how do we move the 8x? Let's see. Over here on this side, it's 7 minus 8x. Or, in other words, 7 plus a negative 8x. So how do we move it? How do we move that minus 8x?
Add 8x.
I add 8x to what?
To 8x.
The best answer we can come up with right there is both sides of the equation. Okay? Because we want to keep our equation balanced, we're going to add 8x on both sides of the equation. Remember, this is like a balance beam or a teeter-totter. You want to keep it balanced, you got to do the same thing on both sides. Okay, so if we push somebody off one side of the teeter-totter, we have to push somebody off the other side of the teeter-totter. Okay, just logic, right? Yeah. So what are we left with on the left? 7. What do we have on the right? Takeaway. I haven't heard of takeaway in a while. Okay, now this should look pretty familiar, right? This is what we were doing like at the beginning. This is like lesson 2. Multi-step equations, maybe lesson 3. So what do we do now? Sarah? Add 17 to each side. So what do we have on the left? 24. What do we have on the right? So far, so good? So we have 24 equals 12x. What should I do now? Rania? Divide what by 12? Both sides of the equation. No, you didn't say. You just said divide by 12. So what do we get on the left? Divide, not subtract. What do we get on the right? X.
Well, wouldn't it be the same if you did x equals 2?
Yeah, if you wrote x equals 2, yeah. So what would be our last step? Check. Check, charge, cash, whichever method you want to use. Everybody go with that so far? Okay. Now, the good thing about these equations with lots of steps to them is you have lots of options for which to do first. The bad thing about these equations is you have lots of options for which to do first. So you have to be careful to make sure that whatever you choose to do first is a legal step and a productive step. You know, it's not taking you backwards. Now we have one with a grouping symbol. Now, you have two options when you have a grouping symbol like that, especially when there's a fraction involved. You could distribute that 1/4 through. That's one option. The other option is to get rid of the 1/4 by multiplying both sides by 4. Now, either one works. Let me tell you when I want to distribute the fraction through. I want to distribute that fraction through if it was going to give me more fractions. In other words, if when I distributed that 1/4 through, if it left me with 2 fractions, then I wouldn't want to distribute it through. But what's 1/4 of 16? 4. That's a whole number. What's 1/4 of 60? Too much clicking going on. 15. Thank you, Caleb. So that's a whole number. So in this case, I don't mind distributing by the fraction because it's going to leave me with whole numbers. Okay, but if it wasn't going to go in evenly, if I was going to get fractions, then I might not do that. I might multiply both sides by 4 to get rid of the 1/4 and save myself some work with fractions. So we just said that we could distribute first, and you guys already gave me the answer. It's going to give me a 4x and a 15, and on the left we haven't changed a thing. So we had a brand new first step. Now we have something that looks almost identical to the last one we did, just different numbers. Right? Variables on both sides, a few different steps. What do we want to do next? Ryan?
We can subtract 4x to 9x.
Subtract 4x from
9x. Oh, both sides.
both sides. What do we have on the left?
5x minus 5.
And on the right? What should our next step be?
Add 5 to 15.
Add 5 to both sides. What do we have on the left? What do we have on the right? What's our next step? See, this should be like second nature by now because we've been doing these steps over and over and over again. What are we left with?
4.
X equals 4. What's our last step?
Check.
Check. I'll let you guys check on your own. I know you will all do that in your spare time. Go back and check the problems we did in the lesson.
Oh yeah.
Let's look at a real world problem. I mean, you guys are teenagers. You don't have any of those, but let's imagine for a minute. Okay? So, a car dealership sold 78 new cars and 67 used cars this year. The number of new cars sold by the dealership has been increasing by 6 cars each year. The number of used cars sold by the dealership has been decreasing by 4 cars each year. If these trends continue, in how many years will the number of new cars sold be twice the number of used cars sold? That sounds like a lot of fun. All right, let's think about this. We're looking for a number of years at when we're going to reach certain patterns with the cars, right? A number of years. Do we know what the number of years is? No. So since we don't know what the number of years is, and we're trying to find the number of years, what should we do? We're going to need to write an equation, but we can't put a number in for the number of years, right? What should we put in instead? I'll ask the questions here. What should we use to represent the number of years? A variable. Since we don't know what the number of years is that we're looking for, we're going to represent it with a variable. So what do we want to represent the number of years with? Y. Okay, let Y be the number of years. Now, whoops, not yours, years. No, number of years. We're comparing new cars and old cars, right? And we want to know when the new cars will be twice the used. That's what they're asking, right? Now, how many new cars did I sell this year? $78. And how is the number of new cars changing? By 6 what? By 6 every year. So that means we need to add 6 for every Y that it goes up. Each year we add another 6. So the number of new cars we have is 78. That's what we're starting with this year. Plus 6 every year. Make sense? Next year there'll be one more 6. The year after there'll be one more 6. The year after there'll be one more 6. So it's 6 times the number of years gone by. That's got to be equal to twice the number of used. Now we need to do the same thing with the used. How many did we sell this year? How many used cars? Well, and what are they? How are they changing? -4, because they're going. The number of used cars is going down. Okay, it says the number of used cars sold by the dealership has been decreasing, so we should subtract 4 every year. So for new cars, we start with 78, and we're adding 6 or selling 6 more new used cars each year. With the old cars, it starts with 67 this year, and it's going down 4 every year. And we want to know when the number of new cars is twice the number of used cars. Does everybody understand how we came up with this equation? Yes? Now we need to solve. What do we want to do first? Okay, we use the distributive property. What's 2 times 67? Okay, what's 2 times -4y? Does this look like something we've done before? What do we do now?
Subtract 6y from both sides.
Okay. What do we have on the left? Okay, and what do we have on the right?
134 minus 14.
What's our next step? I could, but I'm trying to get the y by itself. So you could do that. It's just going to add an extra step if you do. Subtract 134. So that's what we would call, Renee, that's what we call a legal but not necessarily productive step. You're allowed to do that, but it's not going to get you where you want to go. So we subtracted 134 from both sides. What's 78 minus 134?
-56.
-56. What's our last step?
Divide -14 by 4.
Divide both sides by -14, and what do we get for y? 4. So in 4 years, you will sell twice the number of new cars than used cars. Make sense? All right, now for the really fun stuff. Let's look at equations that have lots and lots and lots of solutions, and equations that don't have any solutions. Let's take a look at this one. What might be your first step? Okay, what do we get when we distribute? Now let me ask you a question. Before we take the next step, how could 3x equal 3x plus 12? How could 3x equal 3x plus 12? How could you have one quantity equal itself plus something else? It'd be like saying that I've got 3 $10 bills in my wallet, and Cameron has 3 $10 bills in his wallet, and I have $12 more than he does.
Maybe
Okay.
a credit card.
Doesn't quite make sense. Yeah, there's no money in credit cards, trust me. Okay? Now, let's take one more step just to prove that this is ridiculous. What would we do next to solve this?
No.
Subtract 3x from both sides. And that leaves us with what on the left-hand side? And what, which is just 0, right? 0x is 0. And on the right-hand side?
12.
Okay, how can 0 equal 12? Okay, so we would say that this equation has No solution. No solution. No, not bad at all. When you come up with some sort of contradiction like that, something that can't be true, you have no solution. There's nothing you could plug in for x that would make 3x equal to 3 times x plus 4. No way. Now, let's look at the other type of equation we could have. 2x plus 10 equal to 2 times the sum of x and 5. What might be our first step? Okay, what do we get when we distribute? 2x plus 10. So now we have the equation 2x plus 10 equals 2x plus 10. What could I possibly put in for x that would make that equation true? Sure, 1 would work. What else? 2. Anything else? No, literally, anything else. No matter what you put in for x, that's always going to work out. Right? If we continue the process, you can subtract 2x from both sides. And we get 10 equals 10. As those annoying kids might say, "Doy."
What?
Duh. 10 equals 10, right? Always. No matter what you plug in for x, this works. So you could write this one of two ways. You could say that all real numbers are a solution. Anything would work for x. But this also tells us the equation is an identity. In other words, both sides of the equation are exactly the same. No matter what you plug in for x, it's always going to work out. So we could have some of those situations as well as in our equations. We could have a no solution, or we could have an identity. Any questions? Okay.